Asked to give a guest lecture about some computer vision problems that you are going to encounter if you venture into a emerging market. Some people call it the virtual reality, and some people call it augmented reality and mixed reality. And for the sake of our discussion today, we just call it enhanced reality, right? XR. And my name is Alan Yang, so I lead the AR/VR program at several Berkeley units, and we're going to talk about these opportunities also later in the talk. And also, usually when I give discussions, since this is a guest lecture, I would like to call it a discussion rather than a lecture, because number one, I don't think that what we talk about is going to affect your grades, and number two is that because of the nature of enhanced reality. I really want to make the interaction to be fun and for you guys to participate. So we only have an hour, so all the discussions is going to be very brief. But I think the only way to make the conversation productive is for us to be more interactive, right? So if there's no stage and then we have a more closer distance, I would actually prefer that. But I think that we can always try to create more interactive discussion in the next hour or so. Okay, so let's start. I think that we are at the tail end of this semester. During this semester, you guys probably have familiarized yourself about what computer vision typically can do. For example, for object detection and recognition, 3D reconstruction, building avatar. And doing some oftentimes you can also some of you may have tried doing augmented reality using iPhone, the AR core, and also you can do panorama using image stitching, right? So you guys have seen some of that or most of these applications using computer vision. So when I graduated with my PhD degree in 2006. So these are the problems that people like to solve in 2006, but none of the problems at that time could solve very very good. So in 2006, I don't know if you guys still remember. So if you are working on computer vision, it turns out to be really hard to get a job. The reason is because all these features, so they are nice to have gimmicks. But they are really not must-have features. They are front and center. And I think that AR/VR, what AR/VR excites me is because this is probably one of the markets, one of the product, and one of the problems that computer vision is front and center. You can say that without computer vision, there will not be modern definition of AR and VR. And there are some other cases of AR/VR we can similarly promote our excitement or interest in computer vision. For example, autonomous driving will be another one. Now, for today's discussion, let me use an anatomy of a AR device from Microsoft HoloLens to make my point. So in this case, in order for you to really create an immersive, augmented experience in 3D space, it's not just a single camera hooking up to a computer has to work, but also it has to work with the suite of components. So combined, it gives you the sense of immersion and the augmentation, right? So just take a look at this picture. And then it has see-through displays, stereo see-through displays. So you will see augmentation from two eyes to give you 3D. We're going to talk a little bit about that. And then you're going to have regular RGB cameras. You can use that for whatever that you want, right? So you can do that for your Skype conference. You can take snapshot pictures and so on and so forth. And it has the depth cameras on the top. And then we're going to talk about a little bit about why we need depth cameras in some of the applications. And we also have microphones. So in AR/VR, in order to create immersion, you also have to guarantee that the vision you created, augmented in the space, is consistent with audio sound, right? So if you are augmenting something that is doing certain things in here, it's better make the sound also when you perceive that, it also comes from, you will perceive that it comes from this location, whether it's a click or it is some voice. So everything has to work together, right? So in this case, previously you guys probably have done exercises, course projects for a variety of computer vision problems. I want to in here to have the first take-home message for today is that the main challenge to make computer vision working, what do I mean by computer vision has to work for AR VR? One of the challenge is the so-called motion to photon latency. So in this case, you start, imagine that you are wearing your headset or you are holding up your devices, right? And you are going to, your body is always going to be moving, right? So it's not a stationary computer on the table. As you move, the camera has to, in certain frequency, track your movement. Because if you're going to augment, this is virtual in here. If the tracking is not correctly as I move, it moves with your head, right? So in this case, you need to compensate for that. So as I move, as rapidly as possible, I want the augmentation, contextually to be fixed in 3D location, right? It may not necessarily have to be fixed. For example, if you are building a car racing game, so you want the car to race on this track, right? So this track may be in the physical space. As I am moving around, or multiple people are playing the game together, you have to have a consistent augmentation with respect to your world. So, what is the tolerance for human perception to be able to not differentiate what is real and what is not real? Right? Earlier, I think the entry-level AR VR, so if you look at the market, they always mention about 60 frames per second, which means that from the perception, using turn on the camera to calculate the movement of your body, and then calculate that transformation, and then compensate for whatever you are going to render in computer graphics. So this end-to-end round-trip latency has to be less than 60 frames per second. Now, the ideal case really is more than 90 frames per second, which means that you only have, for processing one frame, the latency about 12 milliseconds. So that is really when you can feel comfortable to wear AR and VR devices for a long period of time. So previously, the entry-level AR VR, because of the cost, prohibitive cost, they stuck with the 60 frames per second, which is already very, very fast, right? So previously, the cameras are running at 30 frames per second. So 60 frames per second is OK for you to experience AR and VR, but you are going to experience a lot of drawbacks, including make your eyes tired and dizziness, and so on and so forth. I think really the bar for you to not be able to differentiate virtual and real object is really at 12 milliseconds, right? So with this number, you have to start counting, right? Including the turning on the computer and then getting the data, doing whatever the processing you have, finish the calculation, and then tell your computer graphics, Unity 3D, start changing the rendering, and then project those things into the display, and all the way to the display finish rendering. This whole loop has to be less than 12 milliseconds. That's the challenge, right? So currently, this problem is not solved. So that actually, if you want to remember one main message for today, forget about the rest. You guys, I think, are very strong, with your backgrounds. If you want to solve AR, VR problems, start with that. If you can find solutions that can really give anybody, right, big companies, startup companies, investors, 12 millisecond round trip for motion to photon latency, and then we are talking, right? For the rest of the class, so we are going to have to assume that you guys have a basic understanding of 3D geometry, rigid body motion, and perspective projection. But we were going to run a 10 minutes, a quick overview, for you guys to refresh your memory. And if you have not heard some of the discussions, you can take notes, and then you can just study by yourself. I think that if you have a solid linear algebra background, you can teach yourself. It doesn't take a genius to do that. So that actually is the beauty of linear algebra. It converts a lot of calculation to basic matrix, or matrix vector, multiplication. As long as you know how to do linear algebra and do it the right way, and you will know the right formulation of most of the problems that we're going to talk about today. And then we're going to talk about AR and VR literature, in the past 60 years. So today is the 6th year, not today. This year is the 6th year anniversary of virtual reality. So the first virtual reality prototype was created in 1958. So we are going to also talk a little bit about that. And then we are going to talk about 3 main issues. So I'm going to highlight that really give you challenges to really being able to achieve 12 millisecond latency. The first one is near eye display, right? So we are doing computer vision as I talked about last time. We always assume that we have a simple camera that connects to a computer, and then we render the result on a laptop, right? Or we are doing a competition. The time is really not your concern. You really care about the accuracy, right? 95% and 99%. But in AR, VR, regardless of the accuracy, when the time clock clicks, 12 milliseconds, every 12 milliseconds, you have to make a decision. Otherwise, you are going to lag. And then you're going to lag, and then so your rendering is going to drift, right? So that's the problem. And the number 2 is the depth cameras. As I mentioned that, HoloLens is one example. And also Kinect sensor. A lot of people are having solving computer vision problems using Kinect sensors and so on and so forth. And then we're going to use gesture recognition as an example. Some of the people in the audience actually participated in this project, and then we are going to talk about what we have achieved. And finally, it's an open invitation that Berkeley has a long tradition of doing open source contribution to the community whenever there is a new thing, right? Whether it is the Unix in the 70s or big data in the 90s, and also deep learning, right, in the 2010 and so on and so forth. So we actually took the same route, and we have a group of students and faculty members participated in developing open source solution for augmented reality. So if some of you guys are really get your hands dirty type of guy or gal, I really encourage you to take a look at what we already have on GitHub. And for all the problems that we talk about, they are already source code. And you can read line by line exactly how they are implemented. And if you have new ideas, welcome to join us. And I would love to see what you have in mind. OK, so 10 minutes of quick overview of 3D geometry. So for the rest of this class, we are going to also assume that objects we are going to either detect, recognize, or augment it going to be rigid body motion, rigid bodies. So which means that we are not concerned about articulated objects or deformable objects. So for rigid bodies, basically what that means is that if you have objects over there, and then you pick 2 points, P and Q, okay? Now, if you move motion, right? So if you have a motion that moves this object in space, in any particular time, the distance between P and Q are fixed, right? So that's the definition of rigid body motion. And if you want to parameterize the points, since you have those points, then you can give coordinate system, right? So each point will, you can be assigning a Euclidean coordinate system. If it's in 3D, so x, y, z. So it's the typical coordinate values for each of the points. And then you take the representation of those points, and then you can calculate its L2 norm. And for rigid bodies, every point pairs, the distance are the same, regardless of the movement. And there's another way to look at rigid body motion, which is that a change of coordinate system, right? So in 3D space, you can fix the origin of your coordinate space in any arbitrary location. And which means that if you have an object coordinate system, which is O over there, and then you have the so-called world coordinate system over there, and then you can very easily calculate the change of their coordinate values from the object coordinate system to the world coordinate system, right? So the transformation is with respect to a 3x3 rotation matrix and the 3x1 translation matrix. How many people are familiar with this? I want to see a show of hands. OK, most of you. OK, so then I will run fast. OK, this one I want to pause. Beware of the left-handed and the right-handed coordinate systems. Because if you're stuck in computer vision, I think you assume that it's always right-handed coordinate system. I can guarantee you that when you have, remember closed loop, what that means is that from the beginning you have cameras. You also have IMU. You also have a depth camera. And then you're going to do the calculation. When you send it to a computer graphics system, oftentimes the computer graphics to render the changes is in left-handed coordinate system. So I have seen almost all projects at the beginning people get stuck. Their calculation is right, but the result just seem off. The first thing you want to tell your teammates is check the coordinate system, whether it's left-handed or right-handed. I have seen everybody bump into this problem. So that's why coordinate system is important. Okay. Now, so when you have rotation and translation, one of the problems for the previous calculation is that there is an affine term, right? So r times x plus t. So the affine term is troubling. Oftentimes, what you can do is to adopt a so-called homogeneous coordinate. So in this case, you can expand your dimension from 3 by 3, is 3 dimension, to a 4-dimensional representation. So the way to do that is that you add a 1 over there, right? So if you multiply this 4 by 4 matrix times this 4 by 1, and then you get exactly rx plus t, right? So because 1 over there multiplied with the t, right? So you get exact the same. Now in this case, if you look at the structure now, so which means this 4 by 4 matrix has very interesting structure. It turns out to be a group structure if you know about linear algebra. So it's a special Euclidean group of dimension 3. So just a name, right? So but if you know about a group, it means several things. Number one is that since it's the group, so if you have a x, and then you first transform x by g2, and then you transform by g1, the total effect of the transformation can be calculated by just calculating the operators, right? So you multiply the two operators, and boom, you get a combined motion that carry you directly from the beginning to the end, right? So you don't have to go through the calculation g1 by g2, right? So that's one of the benefits about the group structure. And number two is you can inverse it, right? So if you move from point A to point B, now my question is how to move back from point B to point A, right? Well, you just calculate the inverse. So that also helps you, mathematically to guarantee that your calculation is correct, right? So there's also a trivial condition, being a group is that, what is it? You have to have 1, right? Now the 1 is also trivial, right? So the 1 is, you just set t equal to 0 and r equal to identity, and then you have a 1 element. So that shows that the special Euclidean group of 3 dimension is a group structure, right? I assume that most of you actually know about this. Now the review number 2 is, now we start with 3D, now we slowly get into 2D, right? So that's computer vision, right? You lose information because computer vision, probably you guys have heard from the first lecture, is solving an inverse problem. So the inverse problem is the following. Now suppose you have a camera, right? So this is the center of the camera. So you always check, right-handed coordinate system. And then you have a point represented in the work coordinate system P, X, Y, Z, right? Now, through the camera system, you got an image picture. So the geometry of modeling how you can get an image out of a 3D world can be represented in its simplest form called the pinhole camera. So in this case, you draw a line from the object in space to also the camera center, also in the same space, right? So the first thing is that you are going to have a transformation of 3D coordinate. It's still in 3D, right? Every point in this line, in this ray, has its own 3D location, right? So then you transfer from the representation x, y, z, and then with respect to the camera coordinate. So that's number one. And number two is that now this ray intersect with your image plane at a point, right? So that point, you have to quantize that into pixel coordinates, right? So there are 2 steps. Now let's see how these 2 steps are done. So number one is that you do a transformation of coordinates, right? From the work coordinate x, y, z to small x, y, z, with respect to the camera coordinate. And then, so this is r, and this is t, right? So if you put this together, so remember the homogeneous coordinate, so we just ignore the last row. The last row is just 0, 0, 0, 1, right? So this actually in computer vision is called extrinsic parameter of your camera, right? And the second term is with respect to the quantization, right? So the quantization means that although if you have a point in image, it's an absolute point, but when you represent that in images, it has a size. What's the size of that, right? So that the fx and fy, tell you about the scale of your quantization. And then cx and cy can move once you have a point, and then cx and cy will allow you to define a origin, right? So if your origin is exactly at that point, you set it like this, and then you will get 0, 0. But however, sometimes when you process images, it sets its coordinates to the left top corner, and in MATLAB it set it in the left bottom corner, right? So different type of coordinate systems. So the cx and cy will tell you how do you start counting the pixels. Either it's from the center or it's from the corners, right? So at the end, when you combine this, so this is also this matrix will be called the intrinsic parameters, right? These days, if you buy a high-end camera, typically you will actually directly get the intrinsic parameters. So those intrinsic parameters will be calibrated for you, right? But however, when I said that, it also means that if you have a variable focal focus of your camera, this one is actually not deterministic because you have to fix the focal length and then your optical group in order for you to determine uniquely the intrinsic parameters. But nonetheless, these parameters these days are very easy to calculate, and you guys can assume that they are given, or take some of the computer vision OpenCV algorithms and checkerboard, and you can actually get it yourself. I'm sure that some of the exercises have allowed you to practice that. So finally is that once you have the pinhole camera, what that means is that now if I only have the image, right? So that's computer vision. Now I lose the information of all of that. I only have a picture. It means that with this point, I don't know the depth, right? So any point on this ray can generate this point by the pinhole model, right? So that presents a problem, a fundamental problem called structure from motion. In the case that pinhole model lose depths in single views, right? And then the obvious solution for that is that why don't we add more views, 2 views and 3 views? So in this case, the structure from motion problem is that assuming that now you have multiple images, and then you also have correspondences, which means x1 and x2 corresponds to p, right? And then how these image pairs that we know corresponding to some points can give you the solution back of R and T, right? So that is structure from motion. That structure from motion will give you the depth, give you back the depth information, okay? And how many of you are familiar with the structure from motion? Okay, almost all of them. So, okay, so then I will run really quick. So this is the hat operator, and basically we are going to annotate cross product u and x, u cross v as a matrix times v. So you can quickly check that this is the skew matrix of u. You can annotate like this with a hat operator, or you can use a square bracket, and then with a subscript cross. There are different ways people annotate that, but it all indicates that the cross product of 2 vectors can be annotated as a matrix, a skew matrix, times a vector, right? And then there are a whole bunch of properties of cross product. Since you guys are familiar with that, I will not go into detail. But with these properties, now we can manipulate the rigid body motion, right? So remember, on the top we have x2 equals rx1 plus t, right? Now the second one is that remember we lost the depth information, which means that we only know image x1 and image x2. I really don't know the scale, right? So their scales are annotated by lambda 1 and lambda 2. So which means that if I convert it to images and then multiply by an unknown scale, which means lambda x2 times small x2 is equal to capital X2, right? We know that the top equation is absolutely true, and then therefore the second equation also holds for equality, but we don't know lambda 1 and lambda 2. We lost the information of lambda 1 and lambda 2, right? So the idea for epipolar constraint is how can we convert a equality condition that is true in the 3D space into a condition that governs images, right? So if we can do that, then we get hold of images, we can recover R and T, right? So if you do a simple calculation, the number one is that if we so for the second line, okay, So if we cross product the both sides by t, right? And you know that the t cross product t equal to 0, right? So that cancels t. But at the same time, we also do a cross product of the first two terms. They are not canceling each out, right? Now the second one is now I cross product, I multiply the left-hand side with x2, right? Now, if you are familiar with the cross product, t cross product with x2 is perpendicular to x2, right? Then you dot product x2, this guaranteed to be 0. So it's a simple property of cross product, and that cancel out of the left-hand side, and then means that the right-hand side should be also equal to 0, right? So we also multiply the right-hand side by x2 transpose. So it gives us actually a equality condition, x2 transpose t hat r x1 equal to 0. So that is so-called epipolar constraint, right? Now, when you have an equality condition like this, so this condition only involves images. It doesn't involve the objects anymore. So as long as you have those image pairs, you can always recover R transpose and T and R from this equality condition, right? Does everybody know how to do that? Since most of you guys raised the hand. Linearly square, right? So you have as many pairs as possible. So this condition is linear with respect to the x1, bilinear with respect to x1 and also x2. So if you have many pairs, and then you can line them up, and then you are solving a linearly square problem. Okay. Now the last one I want to remind you guys is how do you find correspondences, right, in image space? Well, you have to have some similarities, right? So if I look at this point from this angle and from this angle, it has to have certain type of invariance, right? And clearly, so that's actually a fundamental challenge of traditional computer vision. If I pick a point in this, right, you really cannot track it because its appearance doesn't give you any invariance to say that this point looks like white at this angle and looks like white also in another angle. But I can point another point which is also white, right? So you need to have some invariant appearances. Well, the most apparent feature points that you can use is corner points, right? Corner point has been studied extensively since the 70s and the 80s. There are a lot of papers discussing how to calculate corner points. It turns out that there is a very, very cute and easy way of calculating corner points. And then the bonus point is that it does not only give you the corner points, it also gives you the edges and also give you the homogeneous regions. Okay, so I don't know if you guys are familiar with this trick. So if you pick a point in here, right, and then nonetheless you can calculate its gradient with respect to x and with respect to y, right? So you guys know how to do that. Now, and then you can do this calculation, and then you form a 2x2 matrix. And then I want to know what's the condition for this matrix such that if I calculate this matrix around, let's say, this point, it gives me a corner point. It indicates a corner point. What's the condition for this matrix? Anybody take a guess? Yes?
Full rank 2.
I'm sorry?
Full rank.
Full rank. That's correct. Does anybody else get the same idea? Okay. So the easy way to do this is think about it the other way. Now, what happens if it's in here? If it's in here, no matter where you calculate the x, the x gradient or the y gradient, it should be identical the same, right? So it's rank 0. Now, if you have a line, so if you have this line, right? Now, let's say ideally it's along x. So now, if you calculate the gradient along, it's along, let's call this y, along y direction, right? So if you calculate the gradient change along the y-axis, this is 0, right? There's no change, either in this line or in this line. However, if you calculate the x, it has a change, right? Significant change. So if you are calculating this matrix on a point that is right on the edge or around the edge, it gives you rank 1. or mathematically, numerically similar to rank 1. When you calculate its singular values, which means that singular values are significantly different. However, if you are calculating from this one, you can imagine that both the gradient along x and gradient along y, or a rotated version of that, is non-zero, and they better be not uniform. And in this case, so this guy turns out to be rank 2, right? So it means that as the equation says in here, if the second smallest singular value is large enough for g, then it indicates that it's a point, right? And then I'm sure that you guys heard about SIFT. I'm not going to talk about more in here. So you can also do difference of Gaussian to apply different Gaussian kernels, and then you find the local maximum that give you more should I say practical or ad hoc definition of local salient points. Now, once you fix the location, then you are going to use, you can use SIFT feature descriptor to describe it, based on its orientation. And then based on the dominant orientation, you can also rotate to fix that. And then you convert how many vectors are along certain direction into a histogram. And then that will be a histogram vectorization of one of the corner points or edge points. And then you just need to compare the similarity between the 2 points. So the SIFT descriptor of this point looking in this direction will be very close to SIFT descriptor looking at this direction. Versus if you compare the SIFT descriptor of this point versus this point, they are significantly different, right? So this is the way that you can establish correspondences from the two images. Now the last thing I want to talk about is what happens if you still have error, right? So I'm sure that you guys also know about ransack, right? Anybody know about ransack? Most of people, right? So it means that you don't believe at any single pairs. Rather, so you actually try your luck and then try to establish a consensus, right? And then you use, if you're running a 8-point algorithm, which means the minimum you only need 8 points, then you repeatedly sample 8 points, and then you see how many of the rest of the point is in consensus with this model. And then you try many times, and then you find the highest consensus. So this actually is a basic pipeline. In the past 10 minutes, I just walk you through the core pipeline, if you want to build a structure from motion system, right? And what's the problem with that? 12 milliseconds, right? It's a long time, very, very long time. Calculating difference of Gaussian and finding the point, calculating the descriptors, and then trying to establish correspondences, doing ransack, and all these things. It takes a long time. So that is one of the drawbacks of conventional computer vision, right? So if you are interested about geometry, of course, if you are interested about object detection, understanding the activities, you may not actually get into this kind of worm. But that's what we are going to need for today. Now let's switch to, in the next, we have exactly half an hour. So we are going to talk about the main topic for today's discussion, which is AR/VR. So how many of you have tried a AR/VR experience? All of you. OK, great. How many of you watched Ready Player One? OK, half of that. I strongly recommend you guys to watch it. I think that Ready Player One really is going to blow the wind to the sail of virtual reality in the next couple of years. It really illustrated that a future of our humanity really can combine reality and virtuality, right? And if you really think back time in the past thousands of years, from caveman drawing information, knowledge on the wall, our transfer of information has been always in 2D. So I think the significance of virtual reality is that it actually gives you, for the first time, a means to communicate between humans and cyber world, or between human to human, in a realistic 3D world, right? So your canvas is not just a piece of screen in front of you. It can be anywhere around you, right? So think about Google Earth. Right? When you walk on the street, you're actually not looking at your screen. You're actually looking at the stores, the restaurants, the coffee shops you want to go, and then you look at your friends being around, and then you have the augmentation of their information. Not on the screen, but really in the space. I think that is the attraction of either virtual reality and augmented reality. So if we turn back time, as I talk about, so this year, very important and timely, is the 60-year anniversary of virtual reality. So how many of you know about the Sensorama? Not too many people. So this was created in 1958. So what it does is virtually allow you to drive a motorcycle. So it has a vibrating chair. So when you sit on it, it vibrates, based on the road condition. Also, you have handles, motorcycle handles. It also vibrates and also responds to your turning signal. And of course, you stick your eye in the display, and then it let you see the visualization of the street. And then it has something that most of the current systems even don't have. It actually has a smell generator. So it actually simulates, for the particular demo, it actually simulates people driving on the street of Brooklyn. So imagine that you drive past a pizza shop. So you will smell the pizza, right? But if you drive past a suet, probably you will hear, you will smell the smell of the suet from the city. But that really is all the functions of what should be called virtual reality that was envisioned in 1958, right? Now, if you compare today's demo, I don't know if you guys see the Samsung 4D movie experience that strap you on a moving chair and then let you rotate. It's not that different from this one, 60 years before, right? And then also think about Ready Player One. When you guys go watch Ready Player One, think about Sensorama, right? 60 years, still doing the same thing. And this year is also the 50 years anniversary of wearable augmented reality prototype. So in this case, and because, as I said, augmented reality has to respect your world. So that means two things. Number one is that the optics has to be see-through. So not only I see the information, I also need to see the world so that I will see that, oh, I put a pen on my wallet, right? So I have to see the virtual object and also the real object. And then number two is, as I said, I'm constantly moving, so I don't want to bound myself, as a stick in here. So it has to be portable. In 1968, when the first prototype was created by Ivan Sutherland, because the system is so heavy that it actually has a hanger that actually hangs the VR system on the top of the head. And you either use your two hands to hold it, or you want to be hands-free, and then you have to trust the hanger. Without falling and hit you on the foot. And also, it connects to a huge computer in here. But what it does in 1968 is a cube. It's a 3D cube, right? So that's simple, right? So when you move around, you actually see different sizes of a cube, right? So actually, it's very similar to Star Wars, right? So in Star Wars, you see the Death Star projected in front of you, and then you look around, and then you see different aspects of that. So if we really put the past 60 years in a timeline, if you have taken any business class, that actually this is so-called the Valley of Death. Actually, it shows you 3 stages of invention, right? From research and development to commercialization to actually success and as a business. So if we put all the key steps of virtual reality and augmented in this timeline, it started in 1958. I also think out 1977. So that's the first Star Wars, right, movie came out. So that actually was the first time I experienced augmented reality. Although at that time I didn't know about augmented reality. I only know it was called Princess Leia's hologram, right, from R2-D2, right? But that's exactly augmented reality, right? As you can see, from 77 to Ready Player One, right? So really, a long memory lane. And then in the 80s, the first patron sponsors of virtual reality and augmented, because it was so expensive, mainly was from the government and NASA. So think about NASA, right? So you need to perfect skills for astronauts to perform in outer space. But in the real world, you don't have your satellite, you don't have your shuttle. And how do you allow people to build muscle memory? By connecting the vision versus the motion, right? Virtual reality, right? So in the 70s and 80s, NASA actually built a virtual reality lab, particularly for training people to do that. And then we are actually now going to the valley of death, right? So whenever you have a piece of technology, you get people excited, and entrepreneurs and money put in. But the first wave always die on the beach. Trust me, most of the case. So in the 1990s, we have one of the key companies people talked a lot about is so-called virtuality, right? So they actually build those stationary machines that hopefully people can pay to play, either boxing or racing or so on and so forth. And by now everybody knows that the business just died. And then I think the really turning point is around 2012. In this case, companies there are more, I think, has a better understanding about what their customer needs. Customer understanding and customer segmentation. They actually propose a variety of very different forms of virtual reality or augmented reality. The number one actually I think is different from all the past is mobile. It's wearable, right? I think wearable really is the direction that you have to go. If you really continue to bound people connecting to a stationary machine, and then that piece of stationary machine costs you $2,000, it's not going to work, right? So you have to, for example, Google Glass costs about, when it was announced, $1,500. Probably I think that if we get down to half of that price, I think really the form factor of Google Glass can really take off. There are a lot of interesting applications of Google Glass. The Google Glass is actually not a failed product. It's, I think, the targeted customer. We still haven't found the right targeted customer who are willing to pay, and also who actually has a lot of use for that, right? So if you pay a product for $800, you better find a good use case for that, right? Everybody, when you buy computers or phones or any products, you actually internally you have an evaluation, right? If I pay this phone for $500, $800, how much can I use for that, And how much, life experience, it changed me. Can I live without it, or it is a must-have features? I connect with my lecturers, I connect, do my homeworks and check my courses and connect my friends, right? So all these functions has to build in order for AR/VR to really become a household product. And finally, fast forward 2018, we are in 2018, the first mass market advertisement, right, of virtual reality, was Ready Player One. Okay, now. So next, I'm going to really get down to the technical part, right? So it's going to be a little bit dense, but as I said, so this 1 hour discussion only serves as an anchor point, reference point, for you guys to really want to know more about AR/VR, right? By no means we can really explain the technical detail very, very well. And later, I'm going to show you some resources you can continue pursuing, this type of research if you are really interested. I think when you look at this plot, one of the questions you have on the top of your mind is, are we really out of the wood yet, right? Are we going to become a next venture, died in the valley of death, right? So next, I'm going to show you some of the critical technology challenges and how can we fix those. And then to front run what we're going to talk about. So if you are someone that is optimistic, so the ideal scenario is that most of the major challenges currently still constrain virtual reality and augmented reality will be solved around the time of 2020. So wait for 2 years. Now, if you guys cannot wait, just run out of the classroom and start doing your things. Now, if you guys want to wait, you guys can think, what is going to be the world post AR/VR? So as you are listening to this lecture, you have two decisions to make, other than the technical details for you, career. You're thinking about your career. Are you going to take advantage of the 2 years to really solve some of the hot problems, or you start thinking about post AR/VR world, right? So maybe the next Facebook, the next Twitter, right? So how can the human interaction is going to be when we are in Ready Player One, right? So there's a lot to think about. Okay, so the first one is near-eye display, right? So when we have anything that give us information, it starts with the display. Now, when the first generation of VR headset was proposed, especially what I talk about is Oculus, right? It was sold, if you guys remember, for $300. Why it can be sold for $300? Because it actually rip out a typical cell phone display and put it right here, right? So now everybody knows about cardboard, right? So if you have all the components from a cell phone, which right now is dirt cheap, $200 BOM cost, build of material, and then you can just hook it up with a piece of paper and put it in front of you, and then you have virtual reality. At least the gist of it. So the pro of using the LCD, most of the last generation of displays are LCD displays, liquid crystal display. The pros is that it's a mature technology, so it's cheap. It can be built very, very bright, and there's no burn-in effect, right? So which means that these, the later technologies has burn-in. What does it mean by burn-in? It means that if you have a logo that you place in the screen for a long time, when you turn it on, when you turn it off, or you switch to another scene, it looks like the logo remained to be there, right? So that's called a burn-in. Well, the con is that the bad thing for the LCD is that it has actually very, very high latency. It means that from the time that your rendering engine has already prepared the memory for rendering until that you can actually see the image from your eyes, it takes more than 5 milliseconds. Remember the 12 millisecond rule? So if just the display rendering, the display takes 5 milliseconds, you are pretty much out of luck, right? So which means that if you use LCD to render only the last stage of your AR/VR experience, you're already out of the zone, the 12 millisecond zone. So it actually have to push you towards some other solutions. Well, of course, there are some other also drawbacks. Number two is the very low pixel density. It means that when people talk about retina display, what that means is that your human eye cannot differentiate whether the picture in front of you is a combination of a pixel by pixel or it's a painting. It's a beautiful painting, right? So that's called retina display. So the reason is because your visual, your cell, your perception cell has limitation in spatial resolution, right? So we're going to talk about later in here. But however, the LCD, because of the structure, cannot shrink the size of the pixel by too much. And then it has low contrast. We're going to talk about it a bit more. And then has narrow viewing angles. And then I think the latest upgrade for smartphones is to use the active matrix OLED displays like this. Well, the pros is that it's a newer technology. It has a higher contrast because each pixels, because it's an organic compound, right? Illuminescent compound, it can be turned on and off individually. So therefore, it actually has high contrast, which means that two pixels right next to each other, one pixel can be on, another pixel can be off, right? So therefore, give you high contrast. Now, this is the key thing. It has low latency, typically less than 1 millisecond of latency. So that's actually why companies like Apple and other or Samsung, they're upgrading their Apple Watch or iPhone towards OLED. It's because actually it has high contrast and low latency. When you watch videos, it gives you better experience. And then the price coming down, right? So it's still more expensive than this. But the downside is that it has burn-in effect, and then it has organic lifespan. It means that over time, the appearance of those compounds will deteriorate. There's an even worse situation that if you look at RGB, for most of the cases, the green channel deteriorates more than blue and red. So which means over time, your color, which is a combination of RGB, doesn't look right at the beginning, compared to the beginning. And then the last one is that it has green door effect. It means that even if you put OLED display in front of you, and you are going to still see grids of pixels. So that's called the green door effect. So if you're not familiar with that, just think about the advertisement, the billboard, right? So the billboard, if you have an LCD billboard, if you're driving the car really far away, you see a picture. But if you drive up, you see individual pixels. So they are not pretty pictures anymore. So they are just blocks by blocks, right? So that's called the screen door effect. Now, what I believe the fundamental solution to really get a good experience in terms of visual is the so-called micro OLED display. it has extreme low latency, less than 1 nanosecond response time. And then with the very high PPI, PPI stands for pixel per square inch. So typically, the pixels per square inch for LCD is about 500, right? So if you check PPI for your iPhones, it's 500. And this one, 600, 800, and 1,000. This one, micro OLED, can go to 3,000. It's very, very dense, which also means that no screen door effect. But it's very expensive, and then it has burning effect, and it has low brightness. Okay? So now let's go through very quickly. So as I said, in 1973, so this is the first LCD, not smartwatch, digital watch, that really revolutionized the world. I believe that there actually was a Nobel Prize associated with the LCD technologies, not for display, but for some other things. But again, so if you use LCD, you blow it up, you put it in front of you, that's what you see, right? So this is the screen door effect. So in 1973, LCD was a breakthrough, and then fast forward today, it became a bottleneck. Why it became a bottleneck? So again, so very quick. Number one, that LCD typically has a single back plane. So which means it's illuminated all at the same time, all the pixels illuminated, right? In order to see different color, you need to actually have a liquid crystal layer to block the light. So that is the idea of LCD. Now, in order to block the light, you need to apply certain voltage to the top and bottom. So the crystals can be aligned. That introduced two things. Number one is that in order to build a voltage, right, like a capacitor, it takes time. Right? It's not instantaneous. In order to charge a battery or a capacitor, it's not instantaneous. Right? So that's why fundamentally LCD cannot have low latency, less than 1 millisecond. The physics. And number two, the liquid crystal, it aligns to block the light. Therefore, the viewing angle is limited, right? Because it's actually particular for the orientation of the liquid crystal to block the light here. When you're looking at it from different angle, it actually blocks the light going to that direction, right? So that's another limitation. And third limitation, as I said, in a single backplane, so the contrast is not very high. So now if we switch to OLED, so it simplifies the whole stack of processes into, in principle, just 3 steps. So you have a substrate to support everything that you built your thin field transistor array, and then build on top of your substrate. And then this thin field array is going to individually turn on those organic compounds, right? And then you are going to have those compounds. So there is a positive layer and the negative layer, cathode and anode, that pass through the currents through the layer. So the thing you want to remember about LCD and OLED is that the illumination of individual organic compounds, which correspond to pixels, is controlled by the current, and then also controlled by the TFT component, which means that if you turn it on, turn it off, you get instantaneous current. So that's why that you can turn on individual components, and this turn on process can be very, very fast because it's using current. It's not using the voltage. You don't need to wait for the crystal to align each other, right? So that's why it is very, very fast. Now, can we do better, right? So as I said in the third column, so if all this can be built on a silicon wafer, then we can actually encapsulate the entire steps, layers, into a very thin layer directly on the silicon wafer. So this actually is the so-called OLED on silicon. Everything, all these components can be built and encapsulated directly on the wafer. So in this case, this is a solid-state display. And some of the current solutions in the market, you see this one can be 2K, 4K. So they're just as big as a quarter coin, right? Think about you get the 4K TV, right? It's probably this big, right? But now with the OLED on silicon, you can shrink the entire thing onto a display. So that's the technology going towards. In the next 2 years, you are going to see display technologies that looks like this. So I think we are running out of time, but I just have a pop-up question in here. So if you study human vision, you know that the resolution of the human vision to differentiate one pixel versus the other pixel is actually 1/60 degree, right? Now, if you take that in virtual reality, you can calculate if you need a 100-degree field of view per eye, what's the resolution you have to pack into that 100 degree? So what's the resolution for the display, right? You can think about this. So just something for you to think about. OK, so now let's quickly move on. So next, I want you to guys actually do an experiment. So in this case, you close one eye. Let's say close your right eye. And then you put two hands in front of you, right? And you make the two hands to align with each other. Now, in this case, you can see that your second finger is hiding from your first finger, right? But now I want you to close your eye and turn on the other eye. Now you suddenly see the two fingers, right? So that's what I'm talking about. With one eye, you lose the depth information. But with the second eye, with the added on of a second eye, you do see 3D. But that actually is not all. So that's actually called the vergence. But there's another factor called accommodation. Now, let's do this experiment again. Now, I ask you to focus on either this finger or this finger. You will see that if you focus on this finger becomes blurry, right? If you focus on this finger becomes blurry, right? So that means that your eye, when it sees 3D, it actually does two things. Number one is vergence. It actually converges to either finger 1 or finger 2. Once you converges, your pupil also adjusts its focus to focus on that point. Therefore, anything that's not on the depth will be blurry. So in order to really create, now think about virtual, right? So if you want to create something virtual, you also have to satisfy these two cues. If your rendering actually does not provide all the cues, you're actually going to feel a little bit weird, right? So the two cues I talk about first is blur, right? So if you are focusing here, but I render a point over here, your rendering machine, when I'm displaying here, your rendering machine better actually display the correct blurriness, right? And the second one is vergence, right? So you have two images, right? Remember, I talk about two images. And when you're actually trying to show objects in space, you better show two separate images when it converges to the right distance. So here's one problem. The problem is that now, if I'm going to use a AR/VR device to display images, the objects actually are not in real 3D space. So they're actually being displayed on a plane, right? That means that no matter how I change the vergence, the accommodation is always in here. Because my individual eye always tell me that my focal plane, which is most clear place, is in this place. So it created a conflict, right? So remember, this one doesn't have conflict, which means that there's a real object in space. Your vergence and accommodation converge at the same point. Now, in virtual reality, at least for now, you create images on an image display, right? You can actually create these 2 points, ask the people to converge. But people always assume that the display can also always detect, at least for now, that the distance from that point is actually in here. So there is an offset. So that created discomfort, right? So this actually is a plot that compares accommodation to vergence. If they are consistent, no matter you are in infinity or in very close distance, you feel comfortable in this region, if they are consistent. However, if you display your objects in a display screen, so your accommodation is fixed. And then if you are going to display, just like IMAX, right? A snake popping up, or you have a far landscape in the back, you are actually operating in this line. When you're operating in this line, and then if you put people's eye in long time away from this comfort zone, people is going to get sick. So that is the problem. Okay? Now, how to solve this problem? Again, we don't have time. Number one is live field display. Companies like NVIDIA are very aggressively pursuing those technology. So the idea, the concept is that instead of displaying one image like that, why don't I actually put gazillions of displays and I try to recreate all the light rays hitting my eye so that I can do refocusing on the fly, right? So if I do have preserved all the information coming into my eye, like 4D, right? So X, Y, and then also direction. All the direction of light, I preserve it. And then you can actually refocus after the image is being projected onto your eye. So that's number one, but actually it's very, very expensive. There is a better way, there is an alternative way of doing that is to hallucinate. So the idea, so that's actually courtesy to Marty Banks' research in Berkeley, is to actually realize that when I talk about blur, remember when we see color, it's actually not white. It's a combination of blue, red, green, and red. When you have a lens system, the focal distance of different color spectrums actually are different. So, remember in here, if you are using your computer graphics to actually generate different blurriness of blue, green, and red, you can actually drive the human accommodation to arbitrary distance. So that actually is a new technology patented by Berkeley using the visual hallucination to have different blurriness functions with respect to blue, red, and green. So in this case, when you are rendering an animation that you tell people, oh, you should be focusing on this character and as it's moving around. Now, if your whole scene is being rendered using different blurry function, your eye will naturally actually follow this object because of this very, very fine cue that the eye is picking up. Okay, so let me spend a few minutes to talk about depth. And previously we talked about cameras, right? So traditionally, if you want to solve structure for motion, you just get some cameras in the market. But however, today, if you look at the market, start from Kinect, you are going to see depth cameras popping up, right and left, including Microsoft. Sony last year acquired Softakinetic. Intel has its own RealSense. And then there is a startup company, French startup company called ZED, and Google has its Tango. You can see that those major companies, they are not relying on conventional cameras anymore. They're actually building their own camera. And then their own new cameras are depth cameras. And so that's why I think the new depth perception become a new paradigm for computer vision. So there are different approaches for measuring depth directly by the camera. Time of flying, structure light, depth from defocus, that's actually what we talk about. You can actually measure the rate of defocus if you have multiple cameras and each one focus on different distance. You can actually estimate the depth. And then, of course, you can have live field. But let's quickly go through the pros and cons of this depth cameras. The pros of using depth cameras, number one is that the direct depth output. So you don't have to do structure from motion. You don't have to have multiple points. For example, either it's a structure light or time of flight, you do active illumination. You actually project light into the world and then wait for it to bounce back so that you don't need multiple views. And then you can get the depth directly from the camera output. You do not have to put the computation text to the CPU. Number two is that, remember I talked about the features. The depth camera is very good when you are trying to do 3D reconstruction of piecewise world. In this case, most of the world like this, they don't have features. So if you use structure from motion, stereo vision, you're going to have problem. But using the depth camera, active perception, you can actually get very stable piecewise estimation of the 3D. And of course, it works in the dark. Okay? But the cons, it consumes more power, and typically has shorter range than RGB camera. RGB cameras can see very clear pictures 100 meters away, but depth camera cannot because it takes power to illuminate the world. It has lower resolution, more noisy on the edge. So that actually is very different. RGB camera will be horrible to reconstruct planes. It turns out that most of the depth camera, they are horrible in reconstructing the edges. Because when you measure the edges by active illumination, when you shine light onto the edge, because actually it has a cutoff. So the light doesn't consistently bounce back to your camera. It reflects. So therefore, the information for you to calculate the depth on the edge actually is a lot more noisy than on the surface. So that's the trade-off. And then it's typically more expensive. And because it has an illuminator, so it has larger package size, and it doesn't work very well under the sun. Okay? Now, I think we are running out of time, so let me actually just show you an application that we made actually at Berkeley. Some of the students in the class actually be part of that, making it.
OpenArc is an open source augmented reality SDK. The software is designed to power a multitude of core functionalities and a wide range of off-the-shelf products. Currently, OpenArc supports the PMD Pico depth camera and the Intel SR300. These depth sensors could be attached to a variety of hardware such as tablets, helmets, or see-through AR glasses. For today, I'm going to use a helmet setup to free both of my hands. OpenArc is able to accurately determine the location of fingertips in all postures. We're able to do this in real time with no additional sensors on the hand. The algorithm is 98.6% accurate on the standard CVAI hand dataset.
Define what do you mean by visual
the tracking can be done under heavy background interference.
In the depth image, it naturally pops up. But the problem is still that you are going to have cluttered background. Right? So you have to do the first step.
Under these conditions, both hands can be tracked independently while maintaining accuracy and performance.
And then you have to also detect those features. What do you mean by fingertips? And then you also have those valleys and peaks and valleys. And then you also don't have a palm. Right?
We designed OpenArc to support multi-user collaboration. It is able to differentiate between your hand and someone else's hand.
So those numbers are the classification we created to classify really whether it is a handshake or not.
We also support tactile feedback in AR. Here we track your hands even when it is physically contacting another surface.
At that point, this hand, in terms of the raw data, actually melts into the plane.
We created 3 demos to show how you can use OpenArc to create fluid interactions in augmented reality. Here I place some blocks on a surface by physically clicking the surface. I can tilt the book to make the blocks fall off as it would in the real world. We can localize with any arbitrary surface that has features during one time. This time I'm going to place some blocks and move them with a pinch gesture.
Than AR Core or AR Kit from Apple or from Google. And because it's open source, you got to implement, you got a chance to implement your own.
Finally, I'm going to knock them down with my finger. In this demo, I created 2-handed gestures with OpenArc. I can select an object of interest with the 2-finger tap. This brings up the controls that allows me to freely rotate and rescale my object.
So that's the benefit.
I can use a 5-finger gesture to rotate my world.
Because now you're actually getting
and I can use a 10-finger gesture to zoom in on my playing field.
In the air, you can really touch your surface, which is actually what we are accustomed to, right? So we always touch objects on the surface, not grabbing in the middle of the air. All right? So open invitation. I think we are running out of time. I still have a few slides, but we have actually a center, a Vive Center for Enhanced Reality. That actually was a generous donation from HTC Vive, one of the leaders in virtual reality. We have actually have assembled a team of faculty members from different disciplines of research. If you are interested in pursuing AR and VR, please come and talk to us and one of those faculty members. Thank you so much, and I hope that you enjoyed the talk.